Today we're going to be looking at the logarithmic function. Now, on the investigation on the previous page, you're asked to compare y is equal to 2 to the power of x as the exponential function, and then we were supposed to convert it into an inverse of that function, which is x is equal to 2 to the power of y. But we can't solve it in terms of y like we usually do with inverse functions. So in order to do it, like we actually can, but you don't know how yet. And in order to do it, what you need to do is use the logarithmic function. So we're going to be looking at the logarithmic functions. Now, a logarithmic function is the inverse of an exponential function. Now, the inverse of the exponential function with base 2 as an example is y is equal to 2 to the power of x. And the logarithmic function would be base 2 written as y is equal to log base 2 of x. Now, the graph of y is equal to log 2 of x is the same as the graph of x is equal to 2 to the power of y. So you can write them kind of interchangeably. They mean the same thing, and they're going to be graphed the same way. So x is equal to 2 to the power of y is the same, has the same graph as y is equal to log 2 of x. Now, the difference here is this is written in terms of y, which is usually how we like to see our equations. So in general, we can write y is equal to log b of x rather than x is equal to b to the power of y to express the inverse of an exponential function, y is equal to b to the power of x. Now, that sounds completely confusing. I realize that. But once you start converting things from exponential to logarithmic form, it's going to become a lot easier. So there's different terminology that we use when we're looking at logarithmic functions. First of all, if we're writing this in terms of y, then y is going to be the value of our logarithm. X is going to be the argument, is known as the argument of the logarithm, and b, so this lowercase b here, is known as the base of the logarithm. And notice how the argument can never be negative for a logarithm. All right, so the x value, the argument can never be negative here. Now let's look at class example 1, where we have the graphs of y is equal to 2 to the power of x and x is equal to 2 to the power of y. It says they're shown here, but they're really not. And these are the same graphs that were generated from the previous investigation, but we can just plot these in with our graphing calculator. And so this 2 to the power of x looks like this. And watch how it crosses my y-axis at 1. And so I'll call this 1 right here. And it does something like this. So that's my first graph, and the second graph is going to be the inverse of this one. And so it starts here, and instead of crossing at x equals 1, it crosses at instead of crossing at the y-axis at 1, it crosses the x-axis at 1. So it's going to cross here. And if you were to double check that, remember you can always use the draw inverse function in your calculator. And in order to do that, remember you'd use the second function, and then you would press the program button right here, and then we would scroll down to option 8 or just click 8, and then we want to make sure we're using the right function. So we go back to my VARs and go over to option 1, and we want to choose the inverse of the function that we have as y1, and then we enter that again, and then the inverse function will pop up here. Now, where we have x is equal to 2 to the power of y, I'm going to write the label y is equal to log 2 of x beside the appropriate graph. So this is the one we want to write y is equal to log 2 of x beside. Now, we want to complete the table below. So for my function y is equal to 2 to the power of x, we want to state the domain. Now, if we look at the domain, we have x values that can be generated infinitely in the negative direction, but also infinitely in the positive direction. Right, this exponential function is just going to go on forever. And so we could say that the domain is that x is an element of real numbers. For our range, however, we have an asymptote at y equals 0, and so our line's not actually going to cross at y equals 0. And so what we're going to say is that y has to be greater than 0. However, y is still an element of real numbers. The x-intercept, well, if it has an asymptote at y equals 0, then there is no x-intercept, so none. The y-intercept, it crosses at y equals 1. And the asymptote, y is equal to 0. So we're not actually crossing that x-axis here. Now from the inverse of this y equals 2 of x, we have y is equal to log 2 of x. So if we have the inverse function, then all the domains and the ranges are going to be the reverse. So are the x and y intercepts, as are the asymptotes. Everything is just inversed. And so first of all, the domain, now we can see that my values of x don't actually go past 0. So now x has to be greater than 0 such that x is an element of real numbers. And y, if we look at our positive y values, this is just going to go up forever, and it's also going to go down forever. And so our range is going to be y is an element of real numbers. This time we do have an x-intercept. It crosses at positive 1 at x equals 1. However, there's no y-intercept. It doesn't cross the y-axis. And finally, there's an asymptote, a vertical asymptote now, at x equals 0. Now in class example number 2, we're going to be looking at the tables for our previous graph. So our graph of y is equal to 2 to the power of x, and our graph of y is equal to log 2 of x. Now, I'll let you take a look at these values here, but notice that the point 3 and 8 on the graph of y is equal to 2 to the power of x indicates that when x is equal to 3 and my base is 2, so 2 to the power of 3 is equal to 8. And so our x value being 3 is going to correspond to the y value 8. And likewise, when I have my graph of y equals log 2 of x, when I have the inverse point, which is 8 and 3, on that graph, it indicates that when x is equal to 8 and I have a base of 2, then the value of that inverse function is going to be 3. So what statement can be made from the point, so x value negative 2, y value 1/4, on the graph of y is equal to 2 to the power of x? Well, all we need to do is substitute our x and y values here. And so where I have the x value negative 2, I'm going to plug that in for the x value here. And so what we're going to have here is 1/4, which is my y value, is equal to 2 to the power of negative 2. Which, if we look at this makes sense, right? Because if I have 2 to the negative 2, I would, in order to solve and simplify, I'd want to convert this into a positive exponent. And in order to do that, I would have to express it as 1 over 2 squared. And 1 over 2 squared is the same thing as 1/4. So in a similar fashion, what statement can be made from the point, and here we have 16 and 4, 16 being my x value and 4 being my y value, on the graph of y is equal to log 2 of x. Again, all we would need to do is substitute my coordinates into my values for x and y, and 4 is going to be the value of log 2 of 16. Now when I have log 2 of 1, well, let's see where my value 1 was for x. And so this is that function graph of y is equal to log 2 of x. Well, when x is equal to 1, my y value is 0. So log 2 of 1 is equal to 0. And similarly, when my x value, or if we look at my x value being 0 in this case, then we would have 2 to the power of 0 is equal to 1. And the log form for log 2 of 1/8, well, when I had x is equal to 1/8 up here, my y value was 3. So log 2 of 1/8 is -3. And the exponential form of that would be 1/8 is equal to 2 to the power of -3. So again, the x and the y values are what are switching here. They're the inverse functions of one another. So if I have 1/4 is equal to 2 to the -2, well now, if we were to write this in logarithmic form, this -2, which is the x value in an exponential form, becomes the y value of my log form, -2. And the base is consistent for all of these because they're from the same graph. And my x value here, or my argument, as it's known as, is 1/4. And when I have 1/2 is equal to 2 to the -1, remember this x value here becomes my y value. So this is -1, and log 2 of 1/2 is equal to -1. Now with class example number 3, we want to use patterns developed from this previous example. And we want to write the exponential statement 10 cubed is equal to 1,000, but we want to write this in logarithmic form. So with all of these, notice how the bases were always the same. Right? So with exponential form, they always had a base of 2. And logarithmic form, we always had a base of 2 as well. So base of 2 for log and exponential form. So that means that for this example, we know that this is going to be log of 10 because we have a base of 10 right here. Now remember with logarithmic form, they're always written in terms of y. So they always equal the y value. And in this case, the y value here was 1,000. Now, if exponential and logarithmic forms are inverse of one another, then this 3 is my x value, and 1,000 is my y value. But remember, these are going to switch places when we write them in our log form. So this 1,000 is going to take the place of the x in the log form, so that becomes the argument. So log 10 of 1,000 is equal to the y value here, which is going to be 3. Now this pattern would be reversed if we're given the log form and we want to go to exponential form. So now I have log 5 of 625 is equal to 4. So the base remains the same, right? So the base is going to equal 5. So 5 to the power of 4, because that was the y value here, it now becomes the x value, is equal to my x value, which is now going to be my y value of 625. Now with class example number 4, we want to state the inverse of the following functions. And we want to answer in the form of y equals. And so this is just another way of saying, when we say state the inverse of logarithmic functions or exponential functions, is if you're given a log function, they want you to turn it into an exponential function. And if you're given something like this, which is an exponential function, we want to turn it into a log function, a logarithmic function. So let's state the inverse of the following functions, and we want to answer in the form of y equals. So the inverse of this one is going to be y is equal to my base, which is 3, and the exponent here, we don't have a value of y or value of x, so this is just going to be 3 to the power of x. Now here we want to go from an exponential form to a log form, and so we're going to start with y equals, and this is going to be, remember, my base of 8, which is going to be log 8 of x. again, there was no actual numbers, numerical values in order to plug in for my x or y variables. Now, with class example number 5, we want to convert each of the following from log form to exponential form. So log 7 of x is equal to 4. Now here we would have x then is equal to 7, which is my base, to the power of 4. Log 5 of 15 is equal to y, or this becomes my the value of my logarithm, or sorry, of my exponent. So 15, and I have a base of 5 to the power of y. Now this one is a little bit trickier. 5 is equal to 4 times log b of 6. Now notice how I have an operation. Another way I could write this is it would be 5 is equal to 4 times log b of 6. In which case all I need to do is rearrange this. And so I could take this 4, if I'm multiplying by log b of 6, then I could divide both sides by 4. So divide by 4 here, and on the other side as well. So this is going to be leaving me with 5/4 is equal to log b of 6. Now we can solve because we have the value, which is 5/4, which then becomes the exponent, and my argument, which is 6 here, becomes the value, and my base is b, so 5/4. Now we want to convert each of the following from exponential form to log form. So 4 to the power of 3 is equal to 64. Now remember, 4 is my base, so log 4 of the value of my exponent, which is 64, is equal to 3. So the exponent becomes the value, and the value becomes your argument in your log. So again, this one here, the base is going to be 2. The base doesn't change, so this is log 2. And the value here becomes my argument, so that's log 2 of 1/8 is equal to -3. Next, let's look at class example number 7. We want to calculate the value of t if log 2 of x is equal to 3 and log 2 of t is equal to x. Now, what we want to do is we just want to start with one of these logarithms. Now, we want to start with the one that only has one unknown, and that's this first one. So if we look at log 2 of x is equal to 3 and log 2 of t is equal to x, this one has 2 unknowns, and so this is the one we're starting with. Now the first thing we want to do is get this into exponential form. So in converting from logarithmic form to exponential form, this value of my logarithm becomes my exponent. And remember, the base stays the same. And so we would have 2 to the power of 3, which is equal to x. Now, 2 cubed is a number that we can calculate. 2 times 2 times 2, which is equal to 8. So the value of x is equal to 8. So now we have one of our unknowns solved for, and we could then take this and substitute it into my second logarithmic function. So I would have log 2 of t is equal to 8. And now we can solve for t, because remember, 8 becomes my exponent, and my 2 here remains my base. And so t is equal to 2 to the power of 8. And this would be 256. as a quick review, we've now seen how to change forms from log form to exponential form. And if we look at exponential form as y is equal to b to the power of x, and the log form as log of b to the y is equal to x, we can now consider how to write the exponential form in log form. So first of all, we can use this procedure that's outlined here. So you write the exponential form y is equal to a to b to the power of a times b to the power of x as y divided by a. So I take this value of a divided by y is equal to b to the power of x. Now, in order to then change it to log form, remember that the exponent here becomes the value of the log, and the base stays the same. So we would write this as log b, and the value of my exponent becomes my argument. So this would be log b of y over a is equal to my exponent, x. Now I want to change each of the following from exponential form to logarithmic form using that same procedure. So let's look at class example number 8, where I have y is equal to 2 times 3 to the power of x. So the first thing I want to do is I want to isolate this exponent. So 3 to the power of x I want to isolate. So I want to divide by 2. This would be y divided by 2 is equal to 3 to the power of x. Now I can make some changes where I start with log, and I start with my base, which is log 3, and this y over 2 becomes my argument, y over 2, and that's equal to my exponent, which is no longer my exponent, but it's the value by logarithm x. Same thing over here, divide by 7. So this would leave me with h divided by 7 is equal to 4 to the power of k. And my base stays my base. So this is going to be log 4 h over 7, and that's equal to k. And we could do this in reverse as well. So we want to change each of the following from log form to exponential form. So y is equal to ab to the power of x. Now, in order to, what we're doing here is working in reverse. And so the first thing we want to do is go from log form to exponential form. And in order to go from log form to exponential form, remember that the base stays the base. So that's going to be 7. And this is my exponent, that's 7 to the power of x. And this is equal to my argument, which is the value of my exponent, y over 3. And then if I want to solve this in terms of y, I'd need to multiply both sides by 3. And so my final answer, I wrote that kind of weird, is equal to 3 times 7 to the power of x.